So last week, we discussed some basic mathematics of a neural network. We discussed the universal approximation theorem, and we discussed a general way to assess the quality of the model which we have trained. Now, this model depends on some parameters theta, which are typically given by the weights and the biases, etc., of a neural network. And then we have an output from the network, which we call for y tilde. So this is what our model. So the model is given by the architecture of the network. So the network consists of hidden layers. It has an input layer. It has an output layer. In general, the data are labeled. That means that you are training towards reproducing data which have been labeled. We normally call this for discriminative training. So that means that you are going to make a prediction on whether the data belongs to that class or that class. So this is the basics of a neural network and the way we are setting it up. And then we have this loss function, which is the function we optimize. This is the one where we want to drive the gradients to zero. So what we are going to do now is to see how we can actually compute these derivatives by using the chain rules, which leads to the back propagation algorithm. And we're going to look at some simpler examples. And hopefully that gives you the basics. And then in the slides here, you will also find the final equations which need to be coded. And there is a program example as well. But let's baby step you guys through automatic differentiation, because that is a fantastic algorithm. And nowadays we use a library in Python, which is called the JAX, J-A-X, which also vectorizes, does just-in-time compilation, etc. There are similar packages for C++ programmers. There's automatic differentiation. There is the same for Fortran and Julia programmers, etc. So basically all programming languages, they can link up libraries which deal with automatic differentiation. So the layout, as we discussed last time, so this is a typical neural network whose layout we discussed last time. And we will have some input layers with input parameters, x1s down to xn. These are the hidden layers. And then there is an output layer. So we have 3 hidden layers and an output layer. This produces this y tilde, which we saw here. And this y tilde depends on all the inputs which are fed through the network. And everything here has a set of parameters. So that means that we need to set up the derivatives and the gradients for all these parameters, and then use some gradient descent method to train the parameters. So essentially, what we end up with then, when we look at these definitions, is that C here is the typical input to one of these nodes. And this is fed into a so-called activation function. We can write it in this form here. And this is roughly what we discussed last time. So these A's, which I have in that figure, they are now given by some function, which we call an activation function, which often, and in its simplest form, is given by the sigmoid. Then what we are doing is that we want to calculate. So these are just quantities which we are going to need, but these are quantities which now will enter the calculation of final derivatives. So what we want at the end is actually a derivative of this function in terms of the last layer. This is L uppercase letters, the last layer. And these are derivatives which we will come back to. But what I want to do now first is actually to give you a reminder on the chain rule and automatic differentiation. So if we have a function, just to quickly remind you of these derivatives, if we have a function which depends on x and y, where you have a dependency on t in x and y, then we know that the gradient, when I take away the different components, is now simply given by this expression. Hope you don't get offended if I repeat these things. And then if you have a multivariable function, which is the case we have in neural networks, then we will have a function, the x, which may depend on t and s, and y, It may also depend on T and S. And that means that what we end up with then is a vector here multiplied with a matrix. This is actually normally called the Jacobian matrix. And then you simply perform the calculations here. So you know that the df dt would then contain these variables here. So these are quantities which we will play around with. So automatic differentiation means that you can break down all the computations in terms of elementary functions. And elementary functions can be functions like the exponential, sine, etc., but it could also be a computer program, a function you have written. So what we are going to set up is normally what is called a computational graph, and a neural network is actually a computational graph. And if we can break it down like that, then it's easy to calculate the different derivatives. So let's take a look at it. And if you wish to dive a little bit deeper, there is a paper by these guys here, Badin et al., which I've actually borrowed a lot of material from. So this is represented, automatic differentiation is given by a set of repeated applications of the chain rule. Now, one thing which will surprise you is that this actually saves CPU cycles. That sounds counterintuitive, right? Because if you calculate the derivative by a finite difference method, what you often end up doing then is to do more operations. But automatic differentiation, the way it breaks up a calculation, saves you CPU cycles. So let's look at some examples and see if I can convince you that this is actually the case. So again, I hope you don't get offended if I go through some. So I have a simple example here. And derivative is pretty obvious, right? No surprise. Now you could use symbolic Python to translate this one into Python code for you. So what I could do now is simply so you see now, this is a Python code and this is a Python code. So this is what you would also do with Mathematica. So you call Mathematica, you type in a function, and it gives you the derivatives. Actually, this is not the way you should calculate the derivative. So in many cases, like we do with neural networks, we need the function f of x, but we need the derivative as well. So we are calculating the cost function, and then we are calculating the gradients of it in the optimization process. So if you now look at the ways you would do this, and this is why we are going to break this up in smaller operations, elementary operations. So the smarter way, if you now think of this, you can actually define a new function, a, which is x squared. So you pre-calculate a. That means that your function, so here there is no saving. If you go back to the function itself and you calculate the operations, so I have one operations, x times x. That's one multiplication. And then I need to take the exponential. Now, taking the exponential, if you were to count the number of flops, the floating point operations is much more expensive than doing a multiplication. But now I'm counting these as equal operations. So when I say exponential and x squared, I have two floating point operations. Okay, so it's not the correct. It's not a correct similarity because the exponential takes more time. But let's just assume these are two operations which I have. If I then look at the derivative, and if I now just use what SymPy or Mathematica gives me, what you have then, if I now don't think at all, then I have x times x, one operation, exponential, two operations, times x, 3, times 2, 4 operations. So in total, I have 6 operations here, because I often calculate the function f of x and the derivative. So that's 6 operations in total. Okay, does everybody agree with that? Now I can reduce this to 4. And the way you would reduce it to 4, and this is also what you would do with the automatic differentiation, is now we evaluate A, so we pre-calculate it, and we pre-calculate B. So we need that anyway to calculate f. But then when we look at the calculation of the derivative, since we have calculated b, there's no point in doing it again. If you just use a function as it is produced by symbolic Python or Mathematica, you would end up doing 4 floating point operations again and again. It's simple, you get the expression immediately, you plug it into your code. But now you actually end up with 2 operations. So the basics of automatic differentiation is to break down the evaluation of a function and its derivatives in simpler functions. So you will actually have a chain of such functions, and I'm going to set up a computational graph, because a computational graph is essentially what you end up doing when you do a neural network. So if you now look at what we had, and we go back to the derivatives, so this is the expression. We know that the derivative with respect to x is now, when we use the chain rule, is simply this expression which you see here, right? So we have the function which is given by b, which is the exponential of a. And then we have the dfb, which is 1. And that means that when I calculate it, we end up with the same expression which we had before. But now you see, if I've broken this down in the different derivatives, and this is something which I can set up as a graph. But I'm going to set up the graph when I come to a slightly more complicated example. So there are 2 ways, if you look at this expression which you have here, you can now split it either like this or like this. So here you start with the endpoint, and this would be called reverse mode. So you start at the end, and then you calculate the final derivative dA dx. Now, in neural networks, this is the standard. And the reason for that is that a neural network can have many inputs. So you can have an input vector with 10,000 inputs. So if you have a photo of 100 times 100 pixels, you have 10,000 inputs. But you may be doing a classification problem, and you want to classify this image as a house. So it's either 1 or 0. So it means your output is just 1 variable. And that's why you normally start at the endpoint. And we actually start at the endpoint when we have produced the output in a neural network training. And then we put that one into the cost function. And then we optimize the cost function, and then we propagate back. So these are just the 2 modes. So automatic differentiation allows you to do it in forward mode, or the backward mode, or just a reverse mode. Reverse mode is, again, as you can see here, it's a chain rule, but there's nothing but the back propagation algorithm used in neural networks. So this is something which is under-communicated in the community. So many people think that the back propagation is just some fancy algorithm which applies to neural networks, but it is actually application of the chain rule in the reverse mode. Are you with me on these kind of simple things? Okay. So if you now move to a slightly more complicated function, and this is where we are going to set up a computational graph here. So if you look at this function here, you see now that the derivative is given by f with the same expression as you have here. And if I run this with the SymPy, and if I'm lazy, I don't like to type all these codes, I can just paste this into my program, define a function for the derivative, and define a function for the function itself. And then I'm done. But if you look at this now, if you want to calculate the number of floating operations, just let's call them operations. So how many operations do we have in the function f of x? If you just do the counting. So x times x is an operation, plus is an operation, exponential is an operation, a square root is an operation. So how many operations do we have to do in f of x, the function itself? If you do the counting. Yeah, that's 5. And if you look at the derivative, And if you do the derivative without thinking, you just take what SymBio Mathematica gives you and you punch in the expression. So how many operations do you have in the derivative? And remember that division is an operation, right? Yeah, 10. I also counted 10. So at least there are 2 people who count correctly. So we have in total, if we don't think, we have 15 operations. If you call this function 1,000,000 times and its derivatives, then you're doing 15 million operations. So the question is, can we reduce this to half the number of operations? So when I ask this way, it means we can, okay? So let's see how we can do that. And this is how we're going to break this up in simple expressions, which now consist of simple mathematical functions. So if you look at these functions, or the function itself, we now define the intermediate functions. So we have A, which has x as a parent, and I square x. So this is one function. I then redefine B, this is my second function, as the exponential of x squared. I define C as A plus B. And I define D, which is f of x, which is the square root of C. Okay? So that's, so what it means, if we switch a little bit and we want to make a graph, and you will see that this is going to be pretty similar to the way we are going to set up a neural network. So let me just bring up the so the way we would now set this up as a graph is the following. So we have a function f of x, which is given by x squared plus the exponential of x squared. And then I define these intermediate steps, which is now given by x squared. I have my b, which is the exponential of a. Then I define c, which is simply a plus b. And finally, I define f of x, which is equal to function d, which is just equal to c here. So this is what I did. And now I can set this up as a graph. So a neural network would have an input layer. Then we feed this to an activation function with some input parameters. So that means that there's going to be a box here. And that's the box which just squares it. That produces A, like that. Now A is then exponentiated. So that means that I'm having a new box here. So I have exp takes A, and that produces B. Now, these 2 guys, they meet here in a new operation, which is just an addition. And that produces C. Then this is now fed into a new box, which is the square root, which then produces D, which then is the same as F. So when we do a neural network, we're actually setting up the equations in much the same way. So just to give you a kind of parallel here, if you think of a single perceptron model with only a scalar as input, so this is a simple perceptron. So this is just the parallel of what we are doing. In that case, we have an input here, but now there is no hidden layer. There is just a function here, the activation function, sigma. We can call this sigma 1 here, and that produces an output, A1. Now this output is then sent into the cost function, a C, which has some parameters. And here we plug in the target value Y, which we want to compare to this A1. So the C could, for instance, since we have only scalars, it could just be A1 minus y squared. So this is another example of what we call a computational graph. So when we can break down everything in terms of these simple operations, then that is where automatic differentiation really comes to its best, actually. So let's take a look then back at does this sound reasonable? So we just break it down in the graphs with small intermediate steps. So if you then go back to the Jupyter notebook here, and we look at this specific function, we have now the derivatives. So we would have the derivative with respect to a of x, which is just 2 times x. We get a dB dA, which is the exponential of a. You have access to the slide, so if it's going a little bit too fast, you can always revisit the mathematics here. I have dc of a, which is equal to 1 by obvious reasons, because c is just a plus b. And then I get dc dB, and then I get dd of dc, which is given by this quantity, and then df of d. So then I can now calculate the derivatives. So these derivatives are now given by, so I have this derivative with respect to c, and you see the chain rule being applied here. I do the same thing here, chain rule, 1 over 2 square root of c. I take df dA. Now I have to be careful because there is a c dependence and a b dependence. And then I get this quantity. And then finally I have my df dx, which is given by this quantity. And if I rewrite it, I can actually write df dx like this. So if you now look at what I have here, since I need b and d to evaluate the function itself, these are pre-calculated. So my derivative had, I think it was Marcus, right? What? Marcus, that's you, right? No. Yeah, okay. So Marcus said that there were 10 operations which we needed to calculate the derivative. How many do we have now? If you do the counting. So you have pre-calculated things, 1 addition, 1 multiplication, 1 division, 3. So we went from 10 operations down to 3. So automatic differentiation makes use of all these kind of intermediate steps. And since we need to calculate the function itself and the derivative, that means that pre-calculating some of these quantities is something which we will have to do anyway, or should do. Yeah? Yeah. You have to think of those as well. That's correct. But what you need to do, so in a certain sense, automatic differentiation can give you less operations. But when you now want to formalize this, and this is a very good point because that was actually my next point. So if you look at all these operations, there are several operations you need to do here. So what you need to do, the final calculation, is actually to formalize this in terms of this computational graph, which you see from the whiteboard notes. And what you could define then is a set of input variables. In our case, in that example, there's only one, x. So what we have is x1 is equal to x. And then we define intermediate quantities. So these are all the intermediate quantities which we are setting up. And then for this I from L plus 1, actually in our case, this starts with 2 here. So here is 2, 3, 4, and 5. Then you define these elementary functions. So the elementary functions would be x3 as an example, which is g3, which now depends on some parent node, which means that the parent node here is actually the variable a. And then you have the elementary function, which is the exponential. Then when you want to do the calculations, this is what you end up having to evaluate. And that's where you have to count the total number of operations. So from the simple example which you saw previously, you may be fooled a little bit, because that's a case where you would do everything analytically by paper and pencil, and then you can really save operations. But then what you have to look at is actually the number of operations you have in the final calculation. So when you're calculating all these derivatives, what you need then is actually to evaluate the sum, where you have this xj, which is now one of the parent variables. So if you look back at the df of x of I, so one example which you have to look at is this df of a, which is now given by these two guys. And the more variable you have, the more you have to calculate. But automatic differentiation is actually a U breaking down when you can actually express everything as a computational graph. And the various functions can be expressed in terms of elementary functions that can be differentiated. Then automatic differentiation works. When it comes to a neural network, this is normally the case. And you will see that if we go back to that example which we had on the whiteboard. So if you look back at what we had on the whiteboard here. So if you look at that example, this is the case which we're going to look at now. Just a simple perceptron model where we have only scalars as input. There is only one x. There will be parameters w1 and b1. And this makes an output. So there's a function sigma, which then takes in the input, produces an output. And this is then compared to this quantity which you see here. So if we now look at the usage of automatic differentiation, what we end up having to do, if we now look at this example, so in this case, we have an input, which is Z1, which is given by these two unknown quantities. So this is called the weight, and this is the bias, which is set in order to avoid that this, in case this W is 0, that the training stops. The function which we have now is a function of W1, B1, and X. And this is a function we want to optimize. So what we need then is actually to optimize these two quantities. And we want to drive these derivatives to 0. These are the only quantities we have. And that means that I need to use the chain rule. So this is me now breaking everything down into simple operations, where I now have the derivative of the cost function, this dA dC1, since dA1 is actually given by the activation function, which takes C1 as input. So this is a derivative of the activation function times X, which is a derivative of that one. And then I have this derivative here. So you see now what we are doing in order to calculate and optimize these derivatives, we need simply now to use the chain rule. And everything gets broken down into simple operations. And this is where automatic differentiation can be used, because we can break it down in specific operations, where you have simple functions. So this function here is a simple one. We know the derivative. This function here is also a simple one. We have an analytical expression for the activation function. And X is just a variable we are feeding in. And this is normally, so if I just bring it back, this would be the typical operation which we would do. So we have some weights, and at every stage in a neural network, at every layer, we are going to update these parameters. So we feed in a value, an initial value, which can be random, and then we make a feed forward pass. We end up with the function A1 here. And then with that one, we take the derivative of this quantity. And then since we want the gradients for the different weights and biases, we end up with these equations here. Now, let me just sneak in one small thing. I can now add a new layer. So this will be a hidden layer. So my output layer is now given by A2. So this is my output layer. I have the input to the output layer, which is given by the weights and the biases, times the output from the hidden layer. This is the output from the hidden layer. And now you see that the function here is the same, but this A2, but now I need the derivatives for all these quantities. And again, you can break this down in terms of the chain rule. This is a simple case because I have only scalar inputs. If I have more than one X, I will have more weights and biases. This is going to be more complicated. And this will be the next session. I'm going to make a video of that so you can actually follow up from these examples. But you see now when I take the derivatives, I'm just using the chain rule, as you can see here. And what you also note is that you can easily generalize this if you have only scalar outputs. But you see that the result depends on the derivatives of this activation function. And this is where we're going to stop today, because that leads to two of the famous problems in neural networks. One is exploding gradients, which is essentially due to the activation function. If the derivative increases, then the gradients can explode, because you see now that when we go back to the input to the first hidden layer, we actually have a DCW1, which now has two activation functions multiplied with each other. So you can generalize this to many hidden layers, and then you will simply see a chain of these derivatives of the activation functions again and again and again. And if that vanishes, your gradients vanish in the training, and your training stops. So neural network is a feed-forward stage and a back propagation stage. And in every such step, you get an update of the weights and the biases. And if that stops by accident, because the gradients are zero, then the training stops. Or the gradients can explode. And that leads to the exploding gradient problem. This is something which we will discuss. And especially for those of you who are interested in recurrent neural networks, exploding gradient is really a big problem. So in the simplicity which you see here, you have the essence of a neural network. And everything, the back propagation is nothing but automatic differentiation in reverse mode. You can split up all operations in terms of simple functions, and then your final derivatives are obtained by using the chain rule. It gets more complicated, obviously, when we have multidimensional inputs and weights which connect multidimensional inputs with many, many hidden nodes in a given layer. But that's the next part. And then the part after that one is the implementation numerically. So I'm going to make videos of these. So these will be the next videos. So that means that next week we can get started more with more discussion of convolutional neural networks, but also look at the structure of a code for a neural network as well. Any questions? I hope this was not too simple, but this is the basic philosophy behind the training of a neural network. And the back propagation algorithm enters essentially all these algorithms, because a neural network is a building block for most of the algorithms. Okay, let me stop here.